Pleasure to be kicking off the second day of DeepSec. I heard there was already a lot of good content on GSM and other topics yesterday. Hopefully we can continue in at the same pace. GSM is under attack, very clearly so, which is a good thing. It's the first step towards the next iteration of an evolution that's long overdue. A 20-year-old technology that security-wise hasn't been revised at all for those 20 years. And that has been, in the same time period, though, spread to pretty much every corner of this planet. 5 billion active GSM lines currently, all poorly secured. I'm here today with the fabulous Dieter Spar, in his own right, an expert on everything RF and contributor to several GSM projects, open source projects that is. And we today don't want to focus on attacks so much, but rather on analysis tools, giving you the tools to create the next attacks. Over the past year, we have been, though, working on an attack, and this attack was specifically on GSM's encryption. Cryptographically interesting, but perhaps not the only thing you can be attacking within GSM. So all the results we built today were primarily meant to create data so we can launch our cryptographic attacks. However, those very same tools today are available to you, open source, to play around with GSM for whatever analysis you can think of. So this is a talk on tools and how to generate the data on GSM that you are used to seeing on, say, your normal network anyway, right? Perhaps as a little teaser up front and a little backward-looking history over the past year. The GSMA challenged us about a year ago, saying, even if you guys can decrypt our phone calls, you can't record them, right? Which was a true statement back then. We were very much focusing on encryption because previously those GSM guys told us that encryption is what makes the system secure. Now, when we were getting close to breaking that, they suddenly thought something else was what made their system secure. So the GSMA and large number of operators within the GSMA believe that the hardest problem in intercepting calls and listening to your neighbors' phone calls and text messages is not decrypting it once it's on your computer, but rather getting it onto your computer from the air. Before explaining why this is a hard problem, let me try to demonstrate what has happened over this past year. If time permits, I'll, in the end, show how keys are actually being cracked and all that. But let's assume for now that we have a system to decrypt keys, and let's assume we've already cracked the key that our neighbor is currently using on GSM. These keys are being recycled for several iterations, for several text messages, calls, or what have you. So it's a fair assumption that once you have the capability of cracking a key, you know that key. For legal reasons, we have to make this assumption here for a live demonstration because we're not allowed to capture anything off the air that's not specifically meant for our phone to receive. So I'll apply a filter here that filters out everything that this phone couldn't be decrypting. And then I think just statistically speaking, it's pretty much impossible that another phone on this cell uses the same encryption key at the same time. So we should be safe when making this assumption. The tools I'm using here are from a suite called AirProbe. A fairly old idea by now, and a suite of tools that has been growing and been improving over the last years, and that today will make its next evolutionary step. Not the part I'm demonstrating now. Oops, that last part was too much. So sorry I couldn't prepare this, but this key does change maybe once an hour. So 62152C looks good. So what I'm using is the air interface here. It's called a universal software programmable radio. Software radio peripheral, same letters in a different order. So it's what the name suggests, a radio that can be programmed to do pretty much anything RF. And in this case, will be programmed to capture data from one tiny chunk of spectrum where GSM operates and spit it out into the computer, and the computer does the rest in software. I have to do a little hack here. You saw the bash file. I keep restarting this program because the actual live capture gets stuck on some data, and then it has to be restarted. So if anybody dares to send me a text message to this number. Can you read this? I'd appreciate if a couple of people could be sending text message to this now. And let me verify that the key hasn't changed. No, that's still the key. Oh, now the key did change. That is Murphy's Law. Yeah, so no text message I've gotten through. Is anybody from A1 here who's configuring the network as we do this? So I, of course, have to change it over to the other key now, since I'm filtering everything that's not encrypted under the key. Curious by what that's determined, how often it changes, because yesterday it was stable for hours. Oops. Oh, yeah.
Yes.
So, more text messages, please. Yeah, we got something. Okay, so the data as it's being shown here in Wireshark is what the AirProbe tool manages to decode. It will spit out the decoded packages on the command line, but it also will forward it on a local interface, so Wireshark can fetch it from there. And since I'm only decrypting stuff that's sent to this key, so I'm assuming that this is a text message for my phone, and it says, kann man das lesen? Can you read this? Yeah, we can. So this is just a tiny peek into what the GSM tools today are capable of. So I think it's fair to say that we picked up GSMA's challenge, and yes, we now have a radio receiving system, being the USRP, and a signal processing software, being the AirPro, that does everything we need to leverage the capability of cracking keys. Intentionally, I didn't send a text message, but rather I wanted to receive one, since the other direction is still very hard. And we'll now discuss why the signaling exercise is hard, and specifically so on the data the phone sends to the base station. So first, a couple of basics. You saw that there were a couple of packets we were actually capturing, one of which was the text message. All these packets, they belong to a transaction. So GSM is fairly complex protocol-wise, even for simple things like sending over 160 characters of text message. And beyond those messages we saw in Wireshark, there's a couple of more that are needed to get the text message to the phone. So what we see if we captured all the channels, or what does the phone see while say it's receiving a call? The phone will first be pinged basically on a broadcast channel. Phone usually listens to this channel, and the base station that thinks from a past transaction that the phone is within its vicinity will, when receiving a call, first query whether that's still the case. So it will send out a ping and ask the phone, hey, are you still there? It will page it, right? The phone will, if still in the reach of the cell, say, yes, I'm still reachable here. And so not to pollute this broadcast channel any further with the actual transaction, the base station will then request the phone to switch over to another channel. So let's say in this case of the cell we just looked at, please switch over to another time slot on this frequency, because only this one time slot is reserved for broadcast, and we need this to page other phones. So they're all switching over to what's known as an SDCCH, a control channel. On this control channel, again, they have to communicate unencrypted at first, since it's not even known yet what key they would use and all that. So the first thing that's usually happening on a control channel is the base station and the phone agree upon a key. Or if they've previously already agreed upon a key, they'll agree to now use that key for every further packet. So, and that is controlled by the base station. And in Western countries, you should expect base stations to say, please now start encrypting so that your call, your text message are protected. The phone will acknowledge all of this, and only now that they're communicating over an encrypted channel, the phone will be told what's actually happening currently. So far, the phone just did what the base station wanted it, and it doesn't know, is it going to receive a text message, is there a phone call, is there anything else? So now the base station will send the information, hey, there is a call waiting for you. Please get ready to take this call. And for instance, in this packet, you'll see the caller ID, right? Now, call ID is the first piece of really private information that's being communicated here. Who calls whom is supposed to be private. And sure enough, it is encrypted, right? Phone acknowledges this, and again is asked to switch to another channel. This SDCCH2 is supposed to be kept free for other phones, of course, to do these exercises. So the traffic, the actual voice call, is moved to yet another channel. Or as is very common in GSM, to a series of channels that are used one after another. So there'll be a sequence of channels that are used for sequential packets, right? So it will use a channel, I don't know, this cell, for instance, operates on channel 51 time slot 0 is this, 51 time slot 1 is the control channel, and then the traffic channels are somewhere between 950 and 1,000 something, right? Maybe 1,020. And it will be a couple of them if configured well. Now with this cell, that's not the case, but let's assume they actually did configure security. So this could be something like go to channel 900 and then go to channel 1000, and then go to channel 900 and go to channel 1000. So the phone keeps hopping through the spectrum, right? This was initially meant for to improve noise resistance. If there's a very noisy signal on one of these frequencies and all the packets get canceled out, there's typically enough information left from all the other channels to puzzle together the voice call anyway, right? Now, this has recently become a security feature, apparently. And it does increase the complexity of capturing this data. Now, we can easily capture this channel 51, and that's what I just did, since the text messages are being sent here and then the conversation is over. I cannot easily capture channel 51 and every other channel that could be used during a phone conversation, right? These are not predetermined, and the sequence of channels to be used for this specific phone call is communicated in an encrypted message. So unless I have a key cracking capability that allows me to crack this message basically in a millisecond before they switch over and start hopping, I don't know where they will be hopping to. And I'll definitely lose as much packets as are being sent while I'm still cracking the key and trying to figure out what the hopping sequence is, right? So the signal processing difficulty come from having to cover a large chunk of spectrum unless you're able to kind of predetermine the secretly agreed upon hopping sequence. The GSM spectrum is divided in many ways. The spectrum itself is fairly large, and the GSM 900 band shown here is actually the smaller of the two. The 1800 band is much larger in frequency yet. But let's focus on this 900 band that we were just analyzing. First of all, of course, it's divided in frequency for communication to the phone. It's called downlink, and for communication from the phone, it's called uplink. So these are strictly separate. They are tied together though. So a frequency up here for the downlink will be associated with a frequency, with a fixed offset, so that the base station and the phone are always hopping in sequence for their sending frequencies. Now this spectrum, first of all, is divided by operators. In Austria, there's 3 operators, and they have varying chunks of the spectrum. There's some operators more focused on the 900 megahertz band, some operators more focused on the 1800 megahertz band. But there's 4? Who's the 4th? Well, the ones that Wikipedia tells me exist. Let me pull out this. What's Hutch? I don't think Hutch has their own frequencies. They'll be sharing some frequencies. Oh, okay. Well, okay. 3G, completely different story. Yeah. Okay. Oh, interesting. So there's somebody who's actually guaranteed to have 3G calls. Huh. No? Oh, okay. Well, never mind. I thought there was some hope for guaranteed security. So in any event, the A1 operator that my phone likes to roam with apparently has two big chunks of the 900 megahertz band. They are disjoint, maybe for auction reasons that these different blocks were auctioned off. Maybe though for signal propagation reasons that they want to be as noise resistant as possible. So it's good to have frequencies at both ends of the spectrum. So for whatever reason they got assigned these frequencies, they're spread over the 900 megahertz band. And then of these big chunks of spectrum, they allocate a few channels, AFKINs, a few channels to every cell. So the cell that's operating here, that my phone is currently connected to, let's see how many channels it got. Well, I guess it's not disclosing its hopping channels. But yeah, it only has one channel up here from what I could figure out. Oh yeah, exactly this one, the 51. And then it has a couple of channels on the other end of the spectrum where it can hop to, or where it could potentially build a hopping sequence from, which this cell isn't doing. And then any one particular call, as we just saw, gets yet a subset of those. Right? It definitely starts off at the 51, since that's the beacon channel and the signaling channel, but then it will jump somewhere else, right? Like the 1010 or whatever, right? So the requirements for debugging this kind of stuff are vastly different depending on whether you want to debug a single phone call or whether you want to suck down all the data that's coming out of a cell, or perhaps even all the data that's transmitted within a certain operator's allocation, or perhaps even capture everything that's transmitted over GSM ever. Right? And depending on your requirements, you'll need very different equipment. Starting off was an equipment that we saw demonstrated yesterday for the first time, and I'm very excited that this now has become open source. A modified phone, right? A phone is supposed to receive GSM signals, decode them very well in cheap hardware, so it should be the perfect sniffing device. However, a phone, of course, is only supposed to capture one channel at a time, its channel, right? So it can hop very fast among the channels, but only one at a time. If your, let's say, debugging subject is just exactly one phone call that maybe you even know the hopping sequence for, one phone is plenty sufficient. If your debugging subject is a cell like the one outside here that's configured in a way where it kind of uses the same channels over and over again for various calls, maybe from a set of 4 or 5, then those 5 channels can be captured with 5 phones, and that's it. That's probably all you need to capture an entire cell here, not just one call, because it's, again, undetermined where somebody will be hopping to, but all calls on this one cell. And one of these phones will cost you 15 euros, right? So even putting together 10 or 20 of them, doubling up because you want to get the uplink frequencies at the same time too, will still stay within a fairly limited budget, right? So that's kind of the entry to GSM debugging. If you know what you're looking for, if you know what frequencies are interesting, that's probably the way to go. It's also extremely easy to configure with the tools that Sylvain, I think, already committed to the OsmoCombB repository. One step up from there are these devices. As I was saying, they're not specifically meant for GSM, so they're certainly not limited to one channel at a time. In fact, the radio capabilities on these are capable of sniffing huge chunks of spectrum. This one is limited by its connection. It has a USB interface to the computer, and it can only, of course, push over as much data as goes over USB. So a USRP1 will capture you 8 megahertz of spectrum. That is, what's the spacing of the channels? but they're really all used, potentially. What's the maximum packing of channels?
Every other channel.
Every other channel. So we have 2.5 to the megahertz. Yeah, so you get something like 20 adjacent channels with this, instead of just one with the phone. But maybe those 20 channels only include one that's really interesting to you. So this now goes more into wideband sniffing, where you're not interested in one particular cell or one particular phone call, but rather in GSM in general. If you want to derive statistics over how different cells behave, this is a great device. There's a big brother to this device, whose radio front ends are very similar. So it kind of captures the same chunks of spectrum. However, its connectivity to the outside world is a gigabit Ethernet interface now, called the USRP2. And that easily captures 20 megahertz, probably more if you have a very stable daughterboard that doesn't fall off on the edges too badly. So with two of these USRP2s, you can already capture everything GSM 900 in one direction. So with 4 of them, you cover really everything. Every phone call that's going on in your vicinity, uplink and downlink from every cell of every operator. Right? And that's a capability, of course, that not necessarily law enforcement, but more intelligence operations, embassies, these kind of people have been wanting for a long time. And they did build this for a long time. It comes in the form of very custom FPGA boards that are basically the same idea as this, but just scaled up by an order of magnitude, with parallel, very fast AD converters and a much bigger FPGA than what's on here. And in fact, a lot of the processing that AirProp does in software in these devices, it's realized in hardware on the FPGA. So there's boards you can buy. They'll run you up to, say, 100,000 euros. They'll capture everything GSM and process it nicely into bits and bytes and just give you the limited decoded data streams into your computer, right? Nice devices, but clearly too expensive. So with this stuff, over here we're talking something like 700 or 1,000 euros. And that's much more tangible, hence we are focusing in our analysis on increasing the capabilities of exactly these devices. And as they are widespread in the community already for other projects that build up upon them, we hope to be contributing to some other people's research business. But yeah, long story short, these devices do sniff downlink. I think we've already demonstrated this. I moved this up front, so you saw how this captured a text message that was sent to us, and then the AirProp would decode it and show you the process data, right? Wireshark has been increased capabilities to decode everything that actually should be sent over GSM. Now, downlink sniffing has been working for a while now. And let me jump over this slide and come back to it later when we talk about actual key cracking. I don't want to get to details part and why uplink sniffing, meaning also capturing a text message that would be sent from this phone, or capturing the second half of a phone conversation, because that's always uplink and downlink at the same time, of course. Why that is much harder, but can also be targeted with this device. So take it away.
So, sorry. Downlink sniffing or receiving the downlink is not that much a problem. Of course, the operators want that you receive their cells. The antennas are on high buildings or on masts, So you can receive a cell quite easily on a huge range, up to 5 kilometers or even 35 kilometers on rural areas. 35 kilometers is also the maximum range of a standard cell. However, for uplink, it's different. The goal is not that you receive the phone in the whole coverage area, of course. It's only the goal that the BTS can receive the phone. So if the BTS can receive the phone, it's good for it. But someone who is going to intercept or listen to the calls could be at a totally different position. So it's quite hard to receive the signal of a phone if you are too far away. Usually you have a range of several hundred meters if you are on the ground and want to receive a different phone. The reasons for this is the signal is usually not that strong. The intention is the BTS sees the signal of the phone and it tells the phone to send at a certain power level. If the power level is good enough at the BTS, it says, okay, it's fine for me. If it's rather strong, it tells the phone, you can use even a smaller power to send to me because I still can receive you. The benefit of this is that the battery life of the phone is extended. It does not need that much power if you send with lower RF output. Another problem for receiving an uplink phone is that the phone can be between buildings. It can even move. If you are in a car, drive around in a city with huge buildings, the signal varies quite a lot. You have a varying signal, you have this power control from the BTS, and this makes it quite hard for an uplink sniffer. What you can do against this is you use directional antenna. You can use an LNA. This is a low noise amplifier in front of your receiver. This can make it easier to receive the uplink channel of the phone. So what we started to implement some first experiments for uplink sniffing in AirProbe. It's not yet complete ready for a release, but we are very close. What we did so far is we used the USRP1. The USRP1 has the advantage that you can put in two different daughter boards and you need them to receive uplink and downlink at the same time. Carsten already mentioned it, the difference between uplink and downlink is a fixed amount of frequency. For GSM 900 we have 45 megahertz, for GSM 1800 it's even much more, it's 95 megahertz, and you can't receive this with a single board. So you need two of them, and only the USRP1 is capable to, that you can plug in two different boards. If you want to do the same thing with the USRP, you need 2 units. If you wonder what those diagrams are, this is the power, as you can see it on the air of an SMS sent to the BTS. Each of those spikes consists actually of 4 bursts. 4 bursts make up 1 message. So every spike on the first picture is 1 message sent from the phone to the BTS. I will do a short demo now and show you how this looks like in AirProbe. I just need a different computer for this. Okay. I have started Wireshark again. In this case, in this demonstration, I take pre-recorded capture files. Those recordings were made with the USRP1. It was an SMS sent to OpenBSC, to our open source GSM network, and encryption was turned on. I use AirProbe to offline decode those pre-recorded messages. I will start air probe here. This is actually a rather old and slow computer, but it has the benefit that you see the messages slowly coming in. Slowly. It's not useful, of course, for real-time catching, but for demonstration it's quite nice. It's not intentionally delayed, it's simply because it is so slow. It's the signal processing part, which takes quite some power to process. On a modern computer, actually no problem. Several years old, it's a problem. What you see here is the first part, unencrypted, which you can decode without knowing the key. What you see is the phone is telling the BTS that it wants to send an SMS. This is the service request message, some measurement reports, something going up and down. The red, I didn't mention it, the red thing is the uplink. The blue one is what is sent from the BTS to the phone. Red is from the phone to the BTS. The interesting thing starts here. This is the ciphering command. This is where the BTS tells the phone to turn on ciphering. At this point, A51 is turned on, encryption is turned on, and you see here that A51 encryption algorithm is used. From now on, you usually cannot read anything more because you need the encryption key. At this point, Kraken comes in, which will demonstrated by Carsten later, and Kraken can be used with some known text to find out the key. In our case, I know the key, and I now restart AirProbe again using this known key, and it will decrypt now all the messages which are coming after turning on the encryption. Again, slow, but okay. We now see the rest of the messages which were actually encrypted. The interesting thing here, some notification ciphering has been turned on, and here again is our, just wait, I will stop it. We have what we need. Here's our uplink SMS in this case. The SMS text is not contained in any downlink frame because actually an SMS was sent from the phone to the BTS. Yeah, and again. We have our text. As I said, it's just a demonstration with pre-recorded data, but it's some fiddling required regarding the power. But actually, yes, we can sniff uplink traffic, and it's expected to be released in, let's say, the next 3 or 4 weeks. Okay, so far for the demo.
Can I just point out that your operator is charging you for text message, pretending that it's so expensive to send these 160 characters over here, but then actually they're sending 41 messages, one of which is the text message, just to get it across. There's so much overhead in GSM, and this is interesting for tracking, of course, because everything predictable is one leverage point where you track it. 41 messages for one SMS.
Can we switch to you?
Yeah.
We have about 5 minutes, so maybe question and answer sections. We can do this after the second talk. Are you here for the? So let's do the demo, and maybe then in the talk we have more time.
Well, thanks for the moderation. I would take questions anyway now because so as Dieter was saying, it's still uplink sniffing is not completely stable, not as stable as the downlink sniffing where I just plug it in and suck down everything from the spectrum, but it works. It has been shown to work now, and it's being improved. Are there any questions on uplink sniffing or any of the things we've covered so far? Short of that, I would want to talk a little bit about key cracking and why it is possible. So let's actually show how easy key cracking is by now. there's this tool called Kraken that was fed with the rainbow tables. We said we would compute last year at DeepSec, which have been computed in the meantime, which have been put on BitTorrent in the meantime, which have been shipped roughly 100 times all over the world. It's a 2 terabyte hard disk that we're shipping everywhere. So it's a widely spread tool now that eats A51 key stream and spits out keys. So for the messages that Dieter just showed, the uplink messages, we extracted the following key stream. So now this is if you don't yet know the correct key. If you had recorded the C file with the USRP that Dieter showed, and you wanted to decrypt it now, short of owning the phone and just can look up the key. All you do is take a guess of what message was sent, and there's 41, at least something like 30 of them are predetermined and completely deterministic. So take a guess at where one of these was. You compute what data then was used to encrypt it to be in this form over the air, and you feed that the XOR of the two, into this Kraken monster. And it will now try to look up every 64-bit segment in this key stream in 40 tables. There's something like 15,000 lookups in each of the tables. It's massive stuff going on in the background. But it's nicely abstracted away. And I usually get lucky and I crack it on the first burst, which statistically shouldn't be possible, but it's been like this every time so far. And the same here. So it just found two possible keys. There's a lot of nonlinearism in A51, so not every possible key actually is the right key. But to verify that these two keys are actually what we want, we can verify it with a second chunk of data. So there's this key we found at this position in this frame. So and to verify that it actually is the right decryption key, we give it a second frame, so you can check whether that too would be decrypted correctly. And in fact, the key that Dieter typed in does match. So if you had recorded your neighbor's uplink, this will be the tool to now allow you to read the encrypted parts as well, right? Short discussion on why this is possible. I was saying that we feed the Kraken with information that was partly guessed, where we say, okay, we expect this message to always occur at this stage of the setup phase, so it must be encrypted with that and that information, and boom, we get enough information to feed Kraken. Now, it doesn't need to be the case that these 30 or so messages are predictable in GSM. In fact, the GSMA, the umbrella organization that kind of owns the standards, they specified almost 3 years ago that every packet should be randomized, that no packet in GSM, if at all possible, should be predictable. And the standard amendment that they did in 2008 calls for all the padding, the stuff shown in red here, the padding that's now predictable at the byte to be replaced with random numbers. So in this sniff, this is from another conversation, but it basically has the same setup messages in it. Just downlink every message that contains any part of red would not be crackable anymore. Now that in this example only leaves 2 messages, and we were discussing this in length during the GSM training 2 days ago. These messages too could be randomized. However, there's no standard for that yet. So big step forward, putting all the existing key crackers out of the market will be randomize those downlink messages. Next step, very crucial, also randomize the remaining messages, the system information message. Finally, after today, third step, randomize what's coming up from the phone, right? The phones too send predictable information, and the phones too use this stupid predictable padding byte. So there's a lot of work ahead for the GSMA, but at least there is a determined path to much more security in GSM without changing the crypto function we butchered over this past year. With that, I hope we've given you some material for thought, some tools you could be using, the air probe in particular, with soon patches to also sniff uplink. And yeah, thanks for your attention.
Thanks for the good timing. We have 1 minute for one question, and then we have to switch to the next talk. But maybe we can, yeah.
With the patch with randomized padding being so easy, do you think operators really want to secure their network, or do they just don't care?
I think they would want to secure it if it's not very costly. They got to understand that this isn't very costly, right? First of all, and I don't think that's quite understood yet. And they got to understand what large of an effect this could have. Since a few years ago, they had the discussion of what can we do to make our networks more secure. And they were told you can spend X billion dollars to upgrade all your equipment to do better encryption function, or you stay insecure. So back then, they kind of choose insecure, and they're staying with it. The fact that now with a little software patch, is one line of code at a random number, right? They could gain much security. I think this is unknown to a lot of operators. However, some are implementing this right now. So the first operator close to here actually will have this by the end of the year.
And you don't have to patch the phone for it to be...
Now, for all phones are compatible with it. Of course, if you patch the base station, it only applies to all the data that's coming down. So if somebody like Dieter with this directed antenna and with this super duper air probe sniffs your uplink data, that needs to be patched too.